So, what we are going to discuss in this maybe 1.5 hour or so is the basics of reciprocal space and how we can use the knowledge in understanding diffraction from single crystals, mainly epitaxial thin films and layers, from the perspective of the technique that we call as reciprocal space mapping or rocking curve. Because there is a, the earlier approach to characterize thin films used to be use of pole figures, which is still relevant. A lot of people still use it. Pole figure is basically nothing but looking at the stereographic projection from experimental samples and then working out the orientation relations and figuring out whether what is the level of single crystallinity or polycrystallinity in a material is, what is the degree of texture, whether it's how close to being single crystal it is. So I will not talk too much, I will not talk in fact about texture. I think Nilesh will probably look at that at some point of time. I will mainly look at what we call as reciprocal space mapping, which is another way of looking at things like peak positions in more detail, specifically from the perspective of calculating the d-spacings quite accurately, which can help you to determine strain in samples. So this technique is useful for a variety of things. We will only look at, because the time will not allow us to look at many more things, and also a lot of other things are a bit too involved. So we will just look at the introductory aspect of this reciprocal space mapping. So the way we will go about is we will look at the reciprocal space lattice to begin with, and then how can we use the knowledge of reciprocal lattice, combine it with X-ray diffraction, and to look at the X-ray diffraction in a different perspective. I mean, to move away slightly from the Bragg's law and see how it can be applied specifically in the context of single crystals using Ewald sphere. I will briefly touch upon stereographic projection. I will not talk too much in detail about it. I will just introduce them to show you that how stereographic projection can be utilized, for instance, in single crystal diffraction using Laue methods. We will briefly look at what diffraction methods are, and then finally quite a bit of time we will spend on understanding the basics of reciprocal space mapping and rocking curve analysis. The references, reciprocal space mapping and rocking curve is a rather recent advance. I think reciprocal space mapping came into being at about 2000. Companies like Panalytical, they launched their diffractometers like MRD Pro in roughly 1998 or so. If I remember, I started doing my PhD then at Cambridge, and we were earlier working on X-ray diffractometers, which were quite primitive in that sense. And suddenly this new diffractometer came, which had which we called as 4-circle diffractometer, and which could generate these maps, which looked very funny at that time, what they were doing. But actually, so it's not a very old technique. It's about 20 years old technique. So there are no books available as such, but for conventional X-ray diffraction, of course, you can go to BD quality elements of X-ray diffraction. And for X-ray, for reciprocal space mapping and rocking curve, one of the good references I could find is by Paul Fuster. In fact, Paul Fuster is the father of reciprocal space mapping in some sense, because he has worked extensively on this technique. He is from Panalytical Research Lab or Philips Research Labs in UK, and he has written this book, X-ray scattering in semiconductors, which is available on internet as well as off print. So now what is reciprocal space lattice, first of all? Well, the understanding of reciprocal space is important, because in order to understand the diffraction completely and to be able to apply diffraction concepts to a variety of diverse problems, it is not sufficient only to understand Bragg's law and do simple powder diffraction. It is necessary to move beyond that, and that is where this concept of reciprocal space is important. Reciprocal space, a lot of developments have been taken from the quantum mechanics. and basically it was meant to be essential for understanding the propagation of waves, either electrons in crystals or for example X-rays in crystals. So basically whenever you talk about propagation of waves in periodic media, you need to understand the reciprocal space, because remember any radiation has a wavelength lambda, but lambda is not a vector, and most of the phenomena that happens is interpreted in terms of vectors, and that is why we need to take the wave vector, which is k 2 pi by lambda, and that allows us to look at things in a little bit more clarity. So it allows us to look at the quantum mechanical behavior of electrons in periodic structures, and that is where the need arose in the beginning. So essentially, I'm not going to too much into physics of it, but basically the way you look at the waves in reciprocal space is to understand the Fourier transformation of a function. So if you take, so for example, the best definition of reciprocal and how you connect real space to reciprocal space is, if you take the Fourier transform of real space, you will get the reciprocal space. So in reciprocal lattice, basically the crystal and its orientation are represented in 3 dimensions by a lattice of reciprocal lattice points, where each point represents a set of parallel planes HKL. So for instance, if you draw a real lattice here, so let us say so this is your real lattice, and if you draw so in this case, for example, you know that this is 100 plane, all right, this is 200 plane, and so on and so forth. You can keep drawing these kind of planes for real lattice, and the way you look at the planes, as you increase the indices of HKL, you will decrease the d spacing, right, and you keep shrinking the whole understanding in the real space. But the way reciprocal space works is, so in the reciprocal space, for example, if you take this as an origin, this becomes your 100 point, this is your 010 point, and this is your 001 point. In the reciprocal space, if you apply the same thing in reciprocal space, so this will be 100 point, this will be 010 point, this will be 001 point, the next point is 200, which will go at the distance double of your real lattice distance. So this will move out of the lattice, and that is how you can keep building the reciprocal lattice. I will explain how in a short while. So this basically, so now this tells you that in the reciprocal lattice, the crystal and its orientation are represented in 3 dimensions by a lattice of reciprocal lattice points. So these are the reciprocal lattice points 001, 002, 010, 020. So they should be 020, not 002, and so on and so forth. And these are the points which are HKL indices. So 010, 200, 020, 030, and so on and so forth. And if you construct this in 3D, you will get the reciprocal lattice. Now, so basically, you can say that each periodic structure, as far as the structure is periodic, it has 2 lattices associated with it. One is the real space lattice, and this basically describes the usual periodic structure. And the second one you can define as reciprocal lattice, which basically determines that how this periodic structure interacts with the waves. And to look at a little bit more mathematically, any periodic function, basically you can express this in the form of periodic Fourier components. So for instance, a very common entity you can take is the periodic potential of the lattice, and this periodic potential of the lattice can be represented as, let's say, if it's r is the real position vector basically. So it's summation of uk, which is the coefficient of potential, multiplies by some phase difference, which is phase factor, which is exponential of I 2 pi k dot r. So here this k is something which cannot be arbitrary. Only those values of k are allowed which are reciprocal lattice vectors, and hence they are well defined. So let's look at it in a little bit more detail. So we can say that ur is equal to summation over g u. So let's say this, we say that this k is g in reciprocal space. So hence I have replaced this k by g. It becomes for all the reciprocal lattice vectors ug summed over all the reciprocal lattice vectors ug exponential of 2 pi I g dot r. We know that for a periodic lattice any function ur must be equal to u r plus r, where r is the lattice vector, because you know that lattice is periodic. So whatever you see at one position, if you move it by distance r, it should look identical, and that is the periodicity of the function. So if this is true for a periodic structure, then if you replace r with r plus r, you can say that ug exponential I 2 pi g dot r is equivalent to saying ug exponential 2 pi I g dot r plus capital R. From this, what do you get? From this we get that if this definition is true, then exponential of I, there should be a 2 pi I, 2 pi as well. Sometimes what happens is that 2 pi is inbuilt in G, sometimes it's taken out of G. It depends upon whether you are a crystallographer or physicist. Physicist generally, this is the physicist way of taking it, and this is the crystallographic way of taking it. So exponential of I 2 pi I g dot r is equal to 1. So basically this extra factor which is there, this factor must be equal to 1. And if this is true, I can define this direct lattice vector in terms of orthogonal, or let us say non-orthogonal primitive vectors. So it's summation over n1 a1 plus n2 a2 plus n3 a3. And we know that reciprocal lattice vectors G is defined by condition exponential I into G dot R is equal to 1, and this leads us to G dot R to be equal to 2 pi n, where n is some number. Is that okay up to this point? So from this, if this condition is true, where G dot R is equal to 2 pi n, then I can define this reciprocal lattice vector G in terms of primitive reciprocal lattice space vectors B. So I can say that G is equal to summation of mi bi, or in 3D space I can take it as m1 b1 plus m2 b2 plus m3 b3, where b1 b2 are reciprocal lattice vectors. And I define this b1 and b2 as here. So you can see that 2 pi has appeared here. If I didn't take the 2 pi, if I took the 2 pi here, then 2 pi would not appear there. So, so this b1 would be equal to 2 pi into a2 cross a3 divided by a1 dot a2 cross a3, and b2 would be 2 pi a3 cross a1 divided by a1 dot a2 cross a3, and b3 would be 2 pi a1 cross a2 divided by a1 dot a2 cross a3. Now this a1 dot a2 cross a3 is the volume of the lattice, and this is equal to a1 dot a2 cross a3 or a2 dot a3 cross a1, and so on and so forth. So all three combinations are equivalent to lattice volume. So this is the primitive lattice volume of real space, and you can say that a real lattice vector, reciprocal lattice vector b1 is a cross product of the real space lattice vector. So you can see here that if you are talking of if you take for example the b1 vector for reciprocal lattice, it will be the cross product of a2 and a3, which means this and that. So that is how you build a reciprocal lattice, and we'll see how you do that in for a few crystals subsequently. Another way of representing that is that the condition, since you have seen the vectorial relation between two of them, that b1 is nothing but cross product of a2 cross a3, b2 is cross product of a3 cross a1, and so on and so forth, they have to satisfy this relation where bi dot aj is equal to 2 pi delta ij, and delta ij is the Kronecker delta, which takes this value. So value becomes 1 when I is equal to j, and the value is equal to 0 when it is not equal to each other. So, this basically is in consonance with these expressions that you have written here, that B1 is cross product of A2 and A3. As a result, A1 dot B1 is 1, but A1 dot B2 is equal to 0. So, let us say I remove M1, M2, M3. In fact, to come back to crystallography, I write it in terms of HKL. I can write G as reciprocal lattice vector as H V1 plus K B2 plus L B3. So, this is the reciprocal lattice vector, which is based on certain definition, which is the cross product of real lattice vectors. And the length of this reciprocal lattice vector is the reciprocal of the spacing of corresponding real plane. So, this G star HKL is nothing but mod of G HKL, and this is equal to 1 over D HKL. We will look at this in a little bit more detail in the next 1 or 2 slides. So, basically what we are saying here is that if you look at, so this is the vector, this is the vector from origin G 0 1 0. The length of this is equal to 1 over D 0 1 0. That is how you move in 3D space. And so the advantage of this is, see that if you just look at the planes in the real lattice, you keep going inside the lattice, you make the space smaller and smaller. If you want to look at higher indices planes, there is much better way of representing higher indices plane, because you make the space more and more open. So from the perspective of visualization, this is a much better approach than real space. So in summary, you can say that this is a real space crystal lattice, which you define in terms of N1, A1 plus N2, A2 plus N3, A3. You take a Fourier transform, you get a reciprocal lattice, which is made of B vectors, which is HB1 plus KB2 plus LB3, and the condition is the dot product of two of them is related by conical delta. The indices are same, dot product is 1, are different, dot product is 0. And the way they are related to each other is exponential I G dot R is equal to 1. And this comes from the periodicity of the structure. If the structure is periodic, then this is a necessary condition. Okay. So this is, for example, so this I have borrowed from Professor Anand Subramaniam. He has made some very nice illustrations painstakingly. So you can see that these are the real lattice vectors A1 and A2. So this is example of 2D. So if this is A1 and this is A2, what is B1 and B2? By definition, B1 is perpendicular to, so B1, this is B1 and this is A2. So this is, this is B2 and this is A1. So you have gone B1. So this is B1 and this is B2, and you keep building this in 2D space and you will get this reciprocal lattice, which is reciprocal of the real space lattice. Similarly, if you take these two as a vector, so this is a real space vector A1, this is a real space vector A2, and again if you construct the reciprocal lattice, you take the perpendicular to both of these directions and you keep building the reciprocal lattice, remembering that the relation is G is equal to 1 over D in that particular direction. So, so the length of this, each of these intercept keeps increasing as you increase the number of indices. So basically what you have here is you have a real lattice, as Professor Prasad already taught you, and if you take the real lattice, if you put some motif or basis on it, decorate each of the lattice points with some molecule, some atom or group of atoms, you make a real crystal, and from the real crystal what we get is a reciprocal lattice, which is basically a geometrical construct. Okay? In a real lattice, the lattice points in a real crystal structure, each of the lattice point is occupied by an atom or group of atom or molecules, etc. But in a reciprocal lattice, there is nothing like that. There is no atom in reciprocal space. In the reciprocal space, on the other hand, is what is basically if you calculate the intensities using the structure factor, each of the lattice point in reciprocal space is decorated by intensities instead of atoms or group of atoms, etc. So it's basically a hypothetical geometrical space, not something which is decorated with atoms. Rather, what you put there is that putting intensities on these points, the purpose of that is, if you put intensity on this point, it will tell you this point will diffract. If you don't put any intensity on this point, it means that this point will not diffract. And we will see this is very useful, because when you take the reciprocal space construction of variety of lattices, for example, if you take reciprocal space lattice construction of simple cubic lattice, BCC lattice, FCC lattice, the transformation tells you that which planes should diffract and which planes will not diffract. So I'll come to that in a little while. So you construct a reciprocal lattice from real lattice using geometrical concepts or mathematical concepts, and then this reciprocal lattice can be decorated with intensities to give you a reciprocal crystal, I mean, which is again a hypothetical concept rather than a real entity. So for instance, if you follow the same notations where B1 is equal to cross product of A2 cross A3, A2 and A3, and if you take B2 to be equal to cross product of A3 and A1, and so you can see that if you calculate the reciprocal lattice vectors and decorate the lattice in reciprocal space, so this is your simple cubic real lattice, and this is the reciprocal lattice. You can see that in simple cubic structure, all the points are present, 0, 0, 0, 0, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0, and so on and so forth. The only difference that being is that this distance here is 1 over dHKL. So if this was, let's say, 2 angstrom, you have to define a new scale for it, which is an arbitrary scale in inverse of length, and that will keep increasing as you increase the indices. And what it also tells you is that when you build the reciprocal lattice of a simple cubic crystals, what we find is that there are no points which are missing. All the points are present, 1, 0, 0, 1, 1, 0, 2, 0, 0, 1, 1, 2, etc. All of them are present. What it tells you is that from the selection rules, as you must have learned from Professor Prasad's lecture, that for simple cubic structure, there are no peaks missing. All the planes diffract, and so all the HKLs are allowed as far as diffraction is concerned. However, when you do the same thing on BCC, so this is a BCC crystal, you derive the primitive lattice vectors. What are the primitive lattice vectors for BCC? Sorry? What are the primitive lattice vectors for BCC? You will take them as from the corner atom to any of the 3 body centered atoms, or you can take the one of the body center and 2 of the two of them along the axis. And if you construct so basically those are the vectors for a BCC crystal. If you apply the formulas that I told you earlier, that B1 is equal to A2 cross A3 and so on and so forth, you will construct a lattice which is reciprocal lattice of BCC. Now notice here the difference. The difference here is that when you construct a reciprocal lattice here, first point is 0, 0, 0. The next point that you construct is 2, 0, 0. Then you have 1, 1, 0. The next point is 1, 1, 0 or 1, 0, 1 or 0, 1, 1. And then, so the way points are arranged in the space is the first point comes here, then the second point, then the third point, and the fourth point, and so on and so forth. And if you arrange these points in the reciprocal space, what you see is that the intensity at these points basically, which are, so all these points like 1, 0, 0, 1, 1, 1, 2, 1, 0, etc., all of them do exist as such mathematically in the reciprocal space, but the intensities at those points is missing. So what happens here is, basically if you now take the sum of these, this is 0, 0, 0, the sum is even. If you take the sum of these two, 1, 1, 0, which is again the sum is even, and if you keep constructing like this, you will get the points for which, the points which are present in reciprocal lattice are the points for which the sum of H plus K plus L is even. no H plus K plus L is odd, that is equal to odd is present in this reciprocal lattice. You can also see one more, there is another representation of this, is that the reciprocal lattice of BCC looks like as if it's a FCC lattice, and the same vice versa is true for FCC lattice. So basically this also tells you that the selection rule that you obtained from the structure factor by putting the positions in there, by using the reciprocal lattice approach, you can again determine that what is present in a reciprocal space is H plus K plus L is equal to even, which is the diffraction condition for BCC crystal. And similarly, if you do it for FCC, this is a FCC lattice, and if you take the transform for FCC using the same formulas, what you will see again here is that there are the missing reflections are those for which things like 100, 110, these are missing. What does it mean? 100 and 110 means whenever you have mixing of HKL, that is whenever they are not all even or all odd, they are missing. So what you construct here is a lattice with lattice points being at only those lattice points for which HKL combinations are unmixed, not mixed. So again, it basically reinforces the same thing that you derived using the structure factor formula. So this is one utility of reciprocal space, that you can determine for a given lattice what are the lattice points which are going to diffract. So whatever is present in reciprocal space decorated with certain intensity will diffract, others will not diffract. So let's get back to diffraction in terms of what happens, what is the utility of reciprocal space. So if you look at Bragg's law, generally we conceive the Bragg's law in the form of real space, that we say that this is a material with plane of atoms, and X-ray beams comes and hits the crystal at certain angle, and there is a diffracted beam. The diffraction occurs only when the beam is oriented to the set of planes in such a manner so that this path difference is equal to integral multiples of wavelength. And so you write it in this fashion, that n lambda is equal to 2d sine theta, where n is order of reflection, d is plane spacing, and theta is the Bragg angle. Now if you look at this equation closely, when you draw the diffraction pattern appears something like this. So this is your intensity, and this is where you have 2 theta, and you have something like this, and so on and so forth. So this is 2 theta increasing. If you look at the expression, this is lambda is, if I take n to be equal to 1, lambda is equal to sine theta, or I can write this as lambda by 2d to be equal to sine theta. So basically, if you look at this expression, sine theta increasing or theta increasing means that your lambda by 2d is also increasing. So in some sense, what we are expressing here in terms of a very simple expression, lambda is equal to 2d sine theta, it means that what you are measuring here is, so as you increase the theta, what happens to d value? Because the leftmost peak is equal to, because if you now square this, what is it is lambda square divided by 4d square is equal to sine square theta, and this d square is nothing but a square divided by h square plus k square plus l square for a cubic crystal. And what it means is that as the sine square theta is increasing, basically h square plus k square plus l square is increasing. So as you move towards the right, you are moving towards the peaks of higher indices, which means peaks of decreasing plane spacing. So now so this is a very simple representation of diffraction in real space. The way you look at it in reciprocal space is, suppose you imagine you have an incident wave, and each wave is associated with a wave vector. So far we are talking of X-ray beam with a wavelength lambda, but now we talk of X-ray beam having a wave vector, let's say k naught. So this wave vector k naught with the magnitude 1 over lambda or 2 pi by lambda, whichever you prefer, this comes and let's say impinges on 2 electrons, or you can say atoms or particles, periodic grating, and you can write this distance between the vector, the real space vector from B to A is expressed by R, which is n1A plus n2B plus n3C, and you can say that A, B, C are the unit cell translations and n are the integers. So, for diffraction to occur, again you apply the same logic, that the path difference must be equal to integral multiples of lambda. So, if I say that the path difference here is AN, which is this segment, minus BM. So, AN minus BM can be written as lambda multiplied by R dot K naught minus R dot KH. K naught is the incident beam wave vector and KH is the diffracted beam wave vector. And this I can write as lambda R dot delta K. And this must be equal to an integer. So, how do we represent it then? So, basically what we are saying is that UA, let us say this is the R vector. So, if I just say N1, N2 and N3 are nothing but UVW, some numbers, then UA plus VB plus WC dot delta K is equal to an integer. And what it also means then is that A dot delta K is equal to sub integer H, and B dot delta, because remember each of these is an integer as well, UVW. So, as a result, this A dot delta K is equal to H, B dot delta K is equal to K, and C dot delta K is equal to L. And this delta K is the reciprocal lattice vector G. So, you can represent this from these equations. You can also write for each of these two equations, you can also write A by H minus B by K into delta K is equal to 0, and so on and so forth. What this means is that this is possible, this condition, if you determine from these three equations, these three conditions are possible because A is the A translation, B is the B translation, C is these are three translations A, B, C. H, K, L are the intercepts on ABC axis. So, the dot product of G or delta K with this is possible. So, these three conditions are possible only when this G vector is perpendicular to the plane H, K and L. So, if that is true, then you can write that this D H K L is equal to A dot G. So, this is the G vector. A dot G, you can take any of them, either A dot G or whichever one. So, A dot G divided by H into mod of G. You can write B dot G divided by K mod G, you can write C dot G divided by K mod G, any of these three intercepts you can take, and this will basically give you 1 over mod G. So, you have derived the same condition that I told you in the beginning, that the length of reciprocal lattice vector is equal to the reciprocal of interplanar spacing. So, this DHKL is nothing but 1 over mod G. So, this is what we have derived. So, now what you can do is that you now construct a reciprocal lattice, which is, let us say we do that in 2D first. Okay. So, you constructed this reciprocal lattice. So, this is let us say if this is the direction, so this is 100 point, this is 200 point, this is 300 point, and let us say this is 010, this is 020, this is 030, and so on and so forth, and the intermediate points, the points in the mesh will follow the convention summation of these. So, this is 110, this is 210, this is 310, this is 120, 220 and 320, and this will be 130, 230 and 330. So, any of these vectors from the origin, this is the origin 000. So, this vector is G110. If you take to this point, this is G110, 120, and this is nothing but 1 over d 120, and this is 1 over d 110, so on and so forth. You can keep doing. Now you have a reciprocal space where this axis represents that vector 100, this vector represents 010 direction, and you have of course the third direction which I am not put in here. Now let us say the utility with X-rays now. Now let us say you have a X-ray beam entering somewhere from some direction. Okay. So this X-ray beam, if it is a wavelength, if the wavelength is lambda, then corresponding wave vector is 1 over lambda. So this 1 over lambda, depending upon the wavelength, will make some sort of, you can make a circle of radius 1 over lambda, and superimpose, assuming that the wave is lying within this plane, which is possible if you have a single crystal. Okay. I mean, it's possible for polycrystals as well, but it's easy to represent in the case of single crystals than in case of polycrystals, because in polycrystals the reciprocal space will be all mismatched, because one lattice will be in this orientation, another will be in some other orientation. So as a result, you will have too many reciprocal lattice points in this for a polycrystal. Let us say this is a single crystal, this is a reciprocal space, and you have a beam coming along certain direction, crystallographic direction. So what you do is that basically, if you look at this particular point, so basically what you are doing is that this is the incident beam direction, and depending upon the wavelength of incident beam, you draw a sphere whose radius is 1 over lambda, and make this sphere intersect the lattice depending upon the orientation of the beam. The diffraction condition is that from the origin, so if this is the origin of the lattice, the point which diffracts to the origin, let us say if this is the point, if this is the origin, this is the point I want to make it diffract. So this is the reflection I want to achieve. So what you can do here is, this diffraction condition will be followed only when you have a beam coming in such a fashion so that your reciprocal, your sphere that you have drawn must intersect with this point at certain point. Okay? And the center of the beam direction will be, so if this is your center of the Ewald sphere, and if you intersect these 2 points, so basically what you are saying is that this is the incoming beam. So if you look at that figure now, so this is the incoming beam, incident beam. This is the plane with certain d spacing whose reciprocal lattice vector is in this direction. Okay? So it's a kind of little bit of mixing of real and reciprocal space. Incident beam comes and hits the plane, and it gets diffracted obeying the Bragg's condition, that is, the angle between the incident beam and the plane must be equal to the angle between the diffracted beam and the plane, and the angle between the incident beam and the diffracted beam should be equal to 2 theta. So for a particular point P to diffract, it must lie on the surface of this sphere or circle in 2D, which is intersecting the reciprocal space. So if you look at it in 2D, basically sphere will be circle. So this is the circle of radius k naught, which is nothing but 1 over lambda. Since in X-ray diffraction the wavelength remains same after diffraction because it's elastic scattering, as a result the radius of a sphere after diffraction and before diffraction is equal to same, which is 1 over lambda, and from this point, which is the center of the Ewald sphere or circle, to this point, which is the origin of the reciprocal lattice, this is 1 over lambda, and again from this point to the diffracting point, again it is 1 over lambda. They should satisfy this vectorial condition that this g vector, which is the reciprocal lattice vectors, is nothing but vectorial difference of k naught minus kg. This is the diffraction condition which must be obeyed. This is equivalent to saying that lambda is equal to 2d sin theta, as we will derive. But so you can see that if this is true, that from the center of the Ewald sphere to the origin of reciprocal lattice, this distance is 1 over lambda. If this distance is 1 over lambda, if this angle, you know that the angle between the diffracted beam and the incident beam is always 2 theta, then what you can do is that, since we know that what is the length of this vector? 1 by d. This is 1 by d, and this is 1 over lambda. This angle is theta. What is this distance? 1 over d, 1 over lambda into sin theta. So this becomes 1 over lambda sin theta multiplied by 2. And what is this equal to? 1 over d. So 1 over lambda. So 1 over lambda sin theta multiplied by 2 is equal to 1 over, what do you get? Lambda is equal to 2d sin theta. So basically it's the same thing that you say in the real space, that lambda is equal to 2d sin theta. It's a different way of representing. The advantage is that you can now choose the direction of a beam, with respect to the orientation of a crystal, and make any point diffract or not make any point diffract. Basically it is very useful for single crystal diffraction. If you really want to find out exact d spacing of any crystal, what you do is that you collect the diffraction data for each of the point separately. Okay, you collect the diffraction data for each of the points separately by changing the orientation of the beam. Because if you change the orientation of the beam, you will change the orientation of Ewald sphere with respect to the reciprocal lattice. Yeah, it will not diffract. It will not. So the necessary condition is that for any point to diffract, all the points, those points must intersect the surface of Ewald sphere. So this is represented in 2D. Now any crystal is given, any crystal is in, if you look at in 3D, your sphere, all the points which lie on the surface of that sphere, they will diffract. Now the question is, if there are two ways of doing it. Now that you have a reciprocal lattice and you have a Ewald sphere, one is that you have a single wavelength and you make the beam rotate to collect various points. Alright, because a sphere will only intersect a few points for a given orientation. So you need to rotate the beam with respect to the orientation of sample to collect many more points. What is the other way of doing it if you want to collect many more points? Which is the same thing. Okay, either you rotate the beam or you rotate the sample. Lambda different. You choose multiple lambdas. Okay, for most X-ray diffraction purposes, we choose a wavelength which is fixed, which is copper K alpha. But traditionally, what was done was to choose a white radiation, a radiation consisting of more. So another way of doing that is, instead of, basically what we are saying is that instead of rotating the sample or the beam to collect multiple points, you can choose wavelengths of different magnitudes in the same beam and create many more Ewald spheres which will intersect with many more points and giving you many more diffraction data. So the diffraction condition, as I just told, is that G vector is equal to KH minus K naught, and you can and from this geometry you can determine that KH sin theta plus K naught sin theta is equal to G, which is nothing but 1 by D is equal to 2 sin theta divided by lambda, which is the Bragg's law. So for a diffraction, so basically the message is, for a diffracted beam with vector K to be present after diffraction from a plane, let's say this is HKL, the vector K plus G HKL must lie on the Ewald sphere. So these were the Laue equations that we looked at earlier, that G dot A plus B plus C is 2 pi H plus K plus L, or you can say delta K is equal, delta K dot A plus B plus C is 2 pi H plus K plus L. We know that delta K is equal to K naught minus KH, that is equal to G, and if you take, if you square both the sides, you can write this as kh square plus g square plus 2k dot kh dot g, that is equal to k naught square. And we know that since k naught square is equal to kh square and g is equal to minus g, you can write this diffraction condition in another form, that is 2k dot g is equal to g square. This is another diffraction condition which is often given in the physics books, but it basically arrives from the same condition, that is delta k is equal to g.
So what is the limiting sphere?
I'll come to that. So I'm just coming to that now. So we can say that diffraction condition can be written in various forms. One is lambda is equal to 2d sine theta, another is delta k is equal to g, which is in the vector space or reciprocal space, or 2k dot g is equal to g square. We know that k is equal to 2 pi by lambda and d is equal to 2 pi by g, and again this boils down to Bragg's law. The concept of limiting sphere that comes from that, because we say that we know that lambda divided by 2d is equal to sine theta, and we know that sine theta value cannot go beyond plus or minus 1. As a result, you are limited by in this inequality that 1 over d should be either equal to or less than 2 over lambda. And what it means is that this g mod of g should be less than or equal to 2k. So basically this limits the radius of your Ewald sphere. So that is the limiting sphere that you see, that you cannot go over 2k. So diffraction basically will occur from only those planes whose reciprocal lattice vectors lie within this Ewald sphere of radius 2k. So let's say we take an example. So this is quite vague in that some sense. So if we take an example, it will become more clear. So let's say we consider a reciprocal lattice of an orthorhombic crystal with lattice spacing being 3 nanometer inverse for 100 planes and 2 nanometer inverse for 010 planes. It is drawn in such a fashion so that the points in the plane belong to 001 zone. So basically what it means is that the 001 vector is pointing out of the board. Okay. If the X-ray beam with wave number 4 nanometer inverse is incident on the crystal, then what should be its direction to result in a diffraction from 120 type of planes, assuming that the X-ray beam lies within the plane of the figure. If it lies out of the plane of the figure, you will have a little bit of difficulty because you can have incident vector which is out of the plane, diffracting vector within the plane. So you will need to choose the you will need to come out of the plane. So for the sake of convenience, we have taken that the beam lies within the plane of the figure. So how will we do that? So what we do here first is that we construct a reciprocal lattice first. So we are taking 1.010. So this is 000 point. You can take 100, 200, 300, and so on and so forth. You don't need to go beyond too many points, and this is 100 is equivalent to 3 nanometer inverse, and you take another one here which is something like that, which is 4 nanometer inverse, which is 010, 020 and 030. Sorry? Oh, one is 2 nanometer. So let's say I invert it. So I make this, anyway, it doesn't matter, it's 2 nanometer, let's say. So I can take another point somewhere here. So this is 010, this is 020, this is 030, this is 040, and so on and so forth. And I build the lattice. This is next point. and I want to diffract 120 plane. So which is 120 here? This is 120 point, 1 in x and 2 in y. This is the g vector I want to diffract. Now the question is how to superimpose the Ewald sphere or the circle on this plane to find out the direction of the beam. What is the take home message from the previous slide? If you look at the previous slide a little bit more carefully, I have not explained that until now. If you have a defined g vector, and you want that to diffract, remember that this point, the center of the Ewald sphere makes a, if you connect the center of this g, it makes a perpendicular bisector to the g vector. So do you get the hint now? Do you get the hint now? You draw a perpendicular bisector to this, and then you are given the wavelength. Wavelength is 4 nanometer inverse, which means you have to choose a point on this perpendicular bisector in such a fashion so that this distance is equal to 4 nanometer inverse. This is 4 nanometer inverse, so this will automatically be 4 nanometer inverse. And you choose, you draw your Ewald circle in such a fashion so that it intersects with this particular point. So let me get back to, so you can have various orientations. You can have two orientations from which the beam can come. So this is the origin, okay. This is the origin, this is 120 direction, and this is G120. You want to diffract this particular point, you make a perpendicular direction bisector. You can choose a point on this side, or you can choose a point on this side. The Ewald sphere can lie on any of these sides to give you the diffraction condition. So this is the incoming beam direction, or it could be this is the incoming beam direction. So incoming beam can come along roughly 100 direction to give you diffraction from 120 point for a given set of lambda. Okay. Now, and you can have multiple spheres of multiple radiuses if you change the wavelength. So Ewald sphere can adopt various radiuses if you change the wavelengths, and you can cover many more points for the diffraction to occur. So for instance, this is another problem. So you have a reciprocal lattice of orthorhombic crystal, which is shown below, and basically under what conditions it should be possible to have both 120 and bar 100 planes diffracting simultaneously. So here you want to diffract from both 120 and bar 100 planes. So basically you draw the perpendicular bisector to this plane, you draw the perpendicular bisector to this plane, and wherever they intersect, you choose that origin of a Ewald sphere, and this will give you a Ewald sphere with a radius 1 over k, which will satisfy both the planes. But it's going to happen only under certain circumstances and for a given wavelength. It cannot happen for any wavelength that you choose. All right. So this is the utility of basically Bragg's law tells you that you choose a particular combination of HKL, and it tells you that at what angle the diffraction will occur. This tells you that if you draw a reciprocal lattice and superimpose with the reciprocal of the wavelength circle or sphere, superimpose both of them, the condition is that the surface of circle or sphere must intersect with the point on the reciprocal lattice for diffraction to occur. As long as that condition is satisfied and delta k is equal to G, your diffraction will occur. And this allows you to do single crystal diffraction in a very controlled manner, because you have the handle to choose wavelength as well as the orientation. So if you can do that, you can study single crystals in a very meaningful way. Polycrystalline materials are generally difficult. They are a lot more complex in this fashion, because polycrystalline materials will have reciprocal space which will be smeared all over the space, because you have many more reciprocal lattices at the various angles, and they give you many more reciprocal lattice points intersecting with the Ewald sphere. So as a result, you get many more diffraction points. So so this is just a brief introduction to reciprocal lattice and what you can do with it, using how you can use it to understand X-ray diffraction, especially for single crystals. I will come back to it a little later. So if you look at, so this is the origin of the lattice, okay, 0 point. I want to diffract bar 1 0 0 point and 1 2 0 point simultaneously using the same beam. So what basically will happen is that you draw a perpendicular bisector to this plane, you draw a perpendicular bisector to this plane and make both of them merge. So you can say that this will be my incident beam direction, this will be my incident beam direction. For the same incident beam direction, I am able to satisfy delta k is equal to G for this particular point and delta k is equal to G for this particular point, because both the points lie on the surface of Ewald sphere and both the points satisfy the relation k naught minus kh is equal to G.
So the direction will be from the intersection to the origin.
Yes. So from the origin, this intersection point, that is the direction of X-ray beam. Okay. This is not the direction, this is the scattering beam vector. This is also the scattering beam vector. So from the center of Ewald sphere, when you connect to the origin of reciprocal lattice, that is the incident beam vector. From the center of the Ewald sphere to the diffracting point is the diffracting beam vector, and the connection between those 2 points is the reciprocal lattice vector. Okay. So we'll revisit this part a little bit. So perhaps this will spill over in the next section. Okay. So I will not spend too much time on this stereographic projection. How many of you have learnt about stereographic projection earlier? Those who have done my course must have. They should raise their hand. Okay, some of you. Let me just, I think Professor Nilesh Gurao will teach you about it in a little bit more detail, but because I will teach you, I'll cover one slide which is relevant to this, so I thought I'll just include this particular thing. Basically, a stereographic projection is a meaningful tool to depict the angles between the plane normals, and this is very useful to represent the planes and their orientation with respect to each other in a 2D fashion. So let's say you have this set of planes and this is the plane normal. If you put this crystal at the center of a sphere and draw for a particular plane HKL, and the normal of that sphere, normal of those planes, let it intersect with the surface of the sphere and connect this normal, this intersection with the south pole. Okay, this is north pole, this is south pole, this is east, this is west. So connection, so the connecting line between the south pole and the point where normal has intersected, somewhere along the line within the XY plane or within the north east west plane, wherever this point intersects is the pole of a plane. Okay, this is one way of doing it, drawing it, and so if you can do it for one particular plane, you can do it for many more planes. And something like this is achieved for a cubic crystal. So this is a plane HKL, for instance. For cubic crystal, if this is a cube, let's say, okay, if this is a cube, what is the pole that you are going to achieve on the right side. Let us say this is x axis, this is y axis, and this is z axis. So if you look along this, let's say this is the east direction, what are you going to get? One zero zero. So this point will be 100. What is this point going to be? Minus 100. Very good. What is this point going to be? 0 1 0, and this is going to be 0 minus 1 0. And what is this point going to be? 0 0 1, because it is the z axis, which is perpendicular to 0 0 1 plane and perpendicular to 0 0 minus 1 plane. And you can keep building building this plot is a lot more easier, because then by using the angular relations you can just keep putting the points in between. So for example, if you are able to draw 0 0 1 and 1 0 0, somewhere along the line you should have 1 1 0. So if this is 0 0 1 and this is 1 0 0, this should be 1 0 1. Similarly, this should be, if this is minus 1 0 0, this is 0 0 1, it should be minus 1 0 1. And you can keep building this for various crystals. So the advantage of this is by drawing these circles, you can project the poles on these circles, and you can determine the angular relation between the poles by you can of course do the calculation by using the formulas, but this is a graphical way of doing the calculation between the various planes, and this is very useful in X-ray diffraction patterns, especially for single crystals. So another alternative is if you want to project it on a screen, wherever you had drawn the intersection in this middle plane, you can take this on a screen and just extend this whole thing on the screen, and you get a bigger view. So basically what you are doing here is, let's say this is the plane, this is the pole, this is the point of projection, and let this point of projection, which in the previous case was south pole, let this point of projection intersect with the pole and extend it on the screen. Wherever it gets extended on the screen, that is the pole of that particular plane. So basically we are saying the same thing in a different manner as shown in the first slide. This is the figure taken from Kaliti, so this is how they have shown it there. And there are a lot more concepts involved of great circle and small circles. I am not going to details of them, but what I just want to show you, that for a standard cubic crystal, depending upon the crystal orientation, if the crystal orientation is such a fashion that your 0 0 1 is perpendicular to the plane, you will get a projection like this. If your 0 0 0 1 1 was perpendicular, you will get a basically you can achieve the right one from the left one. How can you do that? By simply rotating, right? If you just simply rotate, remember this is same, this is 1 0 0, this is bar 1 0 0, which means you rotate this along this axis, the sphere. And what you are going to do that is, you will move this point here and this point there. So you can see that this point has become 0 1 1, and this point has become 0 1 bar 1, and 0 1 0 has come in the middle. So this is just a very cursory introduction to stereographic projection. I am sure Nilesh will tell you in a little bit more detail. I think we don't have too much time. So and this is a more involved one. You can put all the points and see what different points will be. So basically what this allows you to do is, along these various circles, if you look at all the points which lie on the surface of this circle, you can measure the angles by choosing a standard measurement, using a standard chart, which is Wolf chart or Schmidt chart. If you some standards you can take, you can measure the angles. You can also do one more thing. Not only you can measure the angle, measuring the angle between the charts which lie on this particular circle, which is called as a great circle. This is great circle, right? So on the surface of great circle is easier, but you can also manipulate it to measure, for example, the angle between this point and this point. by doing some sort of manipulation. And this is this you can see in quality how to do it. It's quite easy. The reason why I showed you is that all the points which lie on the surface of a great circle are the points. So can you now connect? Let us say you have a circle, okay, and on that particular circle different planes have points intersecting the surface of the circle. What is the common relation between these points? What could be the common relation?
Same radius.
1 by d is the distance.
No, it has no relation to 1 by d. You see, it has no relation to 1 by d. It's just intersection of a plane perpendicular with some point on the in the space. But the fact that all of these points are falling on one circle. Have you heard of zone axis? Professor Prasad ने पढ़ाया था ना zone axis. Now can you नहीं पढ़ाया आपने? अच्छा आप पहुँच नहीं पाएंगे वहाँ तक. So if you now what is zone axis? Zone axis is the direction which is common to multiple planes. Okay, if you have a vector, let's say you have a vector, right? This is a vector which is a direction. You can have a plane like this. You can have a plane like this. You can have a plane which is coming at some other angle. So there are multiple planes which are intersecting each other, and they all have a common direction. And for all those directions, the dot product of UVW and HKL is equal to 0. So all the planes which lie on the surface of this great circle are the planes for which there is a common zone axis. So it's useful in those circumstances, because when you learn single crystal diffraction, you will see that. I'll come to that in a short while, but this is the purpose for which I wanted to show you. So let me now come to, I'll skip this slide. So there are various diffraction methods by which you do the diffraction. In the Laue method, which is used typically for single crystal, the wavelength is variable. You have multiple wavelengths, you can say white radiation, but the angle, the orientation of the X-ray beam with respect to sample is fixed. Okay, so you don't move the sample, you don't move the beam, but you vary the wavelength. There is another method called as rotating crystal method, in which you keep the wavelength fixed and vary the angle in parts. That is, you rotate the crystal, and this is again useful for single crystal diffraction. And then you have a powder diffraction, which is the most common diffraction method, where you have sample is powder, the wavelength is fixed, but the angle is variable because it's a polycrystalline specimen. You have equal probability of each crystal being aligned to the incoming beam, giving you Bragg condition. So because of multiple orientations of grains, and this is basically the most common method. So let's look at the first two in some detail. So this is the Laue method, which is mainly used to determine the orientation of large single crystals. So what you have here is you have a X-ray beam which hits a single crystal, and depending upon the orientation of planes, it gives you a diffracted beam. Okay. Now this diffracted beam, it could be depending upon the theta. If it's more than 90 degree or more than 45 or less than 45, you can have the diffracted beam coming in the backward direction, or you can have diffracted beam going in the forward direction. Now, because of orientation relations of planes and the fact that many of these planes belong to certain, so if you look at this in some sense, this is like if you now go back to stereographic projection, right? You have an X-ray crystal, you have a crystal, and you're now looking at it, right? So you make a 2D projection. In the similar sense, you have an X-ray beam hitting the crystal, and the beams are being diffracted in different directions. But what they do is that they form these cones, suppose for the forward method where the X-ray angle, where the diffracted beam angle is less than, so angle between the diffracted beam and the transmitted beam is less than 90 degrees. They go in the forward direction, and when you put a screen in between the sample, after the sample on the exit side, the diffracted beam intersects the screen. One of the features that is formed is in the form of a cone. And the central axis to this cone, which is formed on this screen, is the zone axis to all the planes which lie on the surface of this cone. And same thing you do for the backward geometry, where 2 theta is more than 90 degrees, or theta is more than 45 degrees. This is the transmission method of Laue geometry, and this is the reflection method for Laue geometry. So what you do is that basically for since it's a multiple wavelength of diffraction, since it's a multiple wavelength of radiation, you can have many more peaks diffracting in the reciprocal space, because you will have many more Ewald spheres. As a result, this can be used to characterize single crystals to increase the spot density. So for example, if you look at this particular construction here, you have this incident, this screen here, which has certain number of spots. And if you translate the same information to the stereographic projection, you have these diffracting spots D1, D2, D3, D4, D5, and so on and so forth. On this, you can superimpose what is the incident beam direction, what is the transmitted beam direction, and what you can do is that if these 5 spots lie on the, so you need to manipulate now this to the stereographic projection. You need to move around and see which great circle coincides with these 5 spots. Whichever great circle coincides with these 5 spots, which will give you then the information about the zone axis. Okay. So basically what you are doing is that you note down the orientation of sample, that this is the, now you don't remember what the direction, you don't know what the directions are, you just know that this is my sample in this shape, this is the orientation in which I had put the sample, and I get certain diffraction spot. Okay. I superimpose the diffraction spot on a stereographic projection, align it so that I find the zone axis. Then I get back to the sample, I say that I had put the crystal in this direction, this was the zone axis. So this is one direction of the crystal. Okay. But just getting one direction will not tell you the complete picture. You need to get a little bit more information about various other directions. So you change the orientation of crystal or change the wavelength and get many more patterns like this and get many more zone axis. Once you get more than 2 or 3 zone axis, you will be able to find out the orientation of the crystal, what the orientation of the crystal will be. So this is of course a tedious process, it's not as simple as I am making it look, but it requires you to do it requires you to collect the data for multiple times, superimpose on the stereographic projection, do a little bit of analysis here, find out, so these are diffraction spots, correspondingly these are the poles which will fall on the same great circle, and then calculate the angle between the incident beam and the diffract. You remember, if this is the diffracted beam and if this is the pole of the plane, the angle between the diffracted beam and the pole should be 90 minus theta, and the angle between the pole and the incident beam should also be equal to 90 minus theta in the Bragg geometry. Okay. So you need to do a little bit of geometry to align everything so that you are able to do it using stereographic projection to calculate the orientation. So it requires a bit of juggling with the stereographic projection. This is another method of doing single crystal diffraction. You take a single crystal, again here what you do is that your beam wavelength is fixed. So single wavelength is going to hit this crystal. If this crystal was stationary, you will only get a few spots which satisfy the Bragg condition. To increase the number of peaks arising from this particular crystal, you rotate this crystal. As a result, you get this array of spots which correspond to various reflections, and then of course do the analysis of these spots to find out. Sorry. These are, if you look at the diffraction spots will go at various angles, right? So these are the angles for which the beam is almost going in the perpendicular direction. So they make sort of a ring along these directions, perhaps. It's a good question. I'll try to find out what exactly it could be. I am not sure. So what we'll do now is, we'll now look at the reciprocal space mapping, having learnt what this reciprocal space is, what Ewald's sphere is, and we'll see how we can use it for characterization of thin films. So typically for single crystals, earlier we were using Laue methods, which allowed us to have multiple wavelengths. But nowadays what we have is, we have diffractometers with single beam. But instead of having just one orientation of sample, we are now able to have diffractometers where we can rotate the sample in multiple orientations. And this is possible because we have been able to design and make diffractometers which allow the sample rotation along various axes. So for example, this is a typical 4-circle diffractometer where you have an incident X-ray beam of a constant wavelength, and this is the crystal. You can rotate the crystal around its own axis, which is one rotation. You can rotate the crystal with respect to, you can rotate the diffractometer within the same plane as of incident beam. So this is the 2 theta rotation. You can also rotate so this is, let's say, the sample, or let me put it here. This is the sample. So your diffraction beam is coming like this. This is the incident beam, this is the diffracted beam. So you can put a detector which can rotate. This is a 2 theta rotation. You can rotate the sample in this fashion. You can rotate the sample in this fashion, and you can rotate the sample in this fashion. So there are these 4 axes of rotation along which the sample can be rotated along this axis, along this axis, along this axis, and the diffractometer, goniometer rotation, and the detector rotation. So now in these modern diffractometers, you have 4 circles of rotation. That is why they are called as 4-circle diffractometers, which allow you to collect data of various diffraction points using the same wavelength. So this is the typical geometry that you use for polycrystalline material, which is a 2-circle diffractometer. So in this case, you just need to rotate the detector with respect to the beam, and you can also rotate the sample. So only 2 circles are needed. So this is more. Okay, I thought I'll cover the strain and all, but I think Professor Ungar will cover the strain part or polycrystalline materials. Is that correct? Yeah, so I'll skip this. I'll just straight away go to. Thanks. So this is a modern diffractometer that you see in most labs. Just in 1 circle rotation is achieved. This is the fixed sample, and you only make the detector rotate in this direction. This is the pixel detector. So you rotate the detector in this direction. This is just 1 circle diffractometer. And this is a typical 4-circle diffractometer where the cradle rotates in this circle, it rotates along this, the detector rotates in this direction, and the sample can be twisted as well. So these are 4 circles of rotation you can have. So let's get back to high resolution XRD.